All right, today we're cracking open what is, no joke, one of the most important books in modern software engineering, designing data-intensive applications. We're going to skip the code and get right to the huge ideas that power pretty much every single service you use every single day. Let's get into it. I mean, really think about it for a second. Every time you stream a movie, order some food, or just send a quick message, there's this invisible, unbelievably complex machine working in the background. And this machine, it has to be reliable, it has to be fast, and somehow it has to work for billions of people all at once. So where does something like that even begin? You know, every massive application we use today started out just like this. One simple idea running on one simple server. It's clean, it's easy to understand, and for a little while, it works perfectly. But then something both amazing and honestly terrifying happens. You get popular. And that one simple server, it turns into, well, this. A sprawling global puzzle of databases and caches and services that all have to work together perfectly. This right here is the real challenge, managing that overwhelming complexity. So how do engineers even start to solve this? Well, they begin by preparing for the absolute worst. You see, the first rule of building any big system is you just have to accept that things will break. It's not a question of if, it is always a question of when. And that brings us to the first core principle we need to understand: reliability. So let's go back to our one lonely server. What happens if its hard drive dies? Or the power goes out? Or, and this is a big one, what if an engineer just makes a tiny mistake in the configuration? By the way, that's actually the leading cause of outages for huge internet services. Well, the answer is pretty simple. Everything just stops. Your app is offline. This is the first big crisis every single growing application has to face. So here's the key takeaway. As the book puts it, reliability isn't about trying to prevent every single failure, because that's impossible. It's about building a system that can take a punch, that can tolerate faults, and just keep on working correctly anyway. It's about building resilience right into the DNA of your system. But how do you do that? Well, the main trick up your sleeve is something called replication. And the idea is actually wonderfully simple. Instead of having just one copy of all your data on one machine, you keep identical copies on a whole bunch of machines. It's like having a team of clones ready to jump in the second something goes wrong. And this just lays it all out, doesn't it? Before, a single failure was a total catastrophe. Now, with replication, if one server goes down, no big deal. Another one just seamlessly takes its place. The app stays online, the data is safe, and, this is the most important part, your users probably never even noticed anything went wrong. So you've survived failure. But that just creates a brand new and much better problem, the problem of success. Okay, so you did it. You built a reliable system, it doesn't crash, people are loving it, and they're telling all their friends about it. This brings us to the second massive challenge: how to handle the load when your app gets wildly popular. In the beginning, everything's cool. You've got a nice, steady, totally manageable number of users. Your system, now that it's all replicated and reliable, is handling the traffic just fine. But on the internet, as we all know, things can change pretty much overnight. And then, bam, this happens. Your app goes viral, and suddenly you don't have 10 times or 100 times, but maybe 1,000 times the users you had yesterday. Your servers are getting absolutely slammed with requests, and everything starts to slow down to a painful crawl. This is the scalability crisis. And that's exactly what we mean when we talk about scalability. It's all about a system's ability to handle that kind of explosive growth. A scalable system means you can just throw more resources at it to handle more traffic, and the performance stays great. The goal here is to make sure your 10 millionth user has an experience that's just as fast and just as snappy as your 10th user did. Now, what's so cool about this is that it shows the two basic paths you can take. You can scale up, which means you just buy a bigger, faster, way more expensive supercomputer. Or you can scale out, which means you spread the work across a whole bunch of smaller, cheaper machines. And yeah, scaling up might seem simpler at first, but scaling out is the only way you can get to the massive global scale of the apps we use today. So we've scaled out. We have hundreds, maybe thousands of servers spread all over the place in different data centers. Our app is reliable, it's scalable, and now it has users all over the world. And this leads us to our third and maybe the most mind-bending challenge of all, dealing with the actual physics of a distributed world. So you have to ask the question, what happens when you've got a user in London, another one in Tokyo, and a third in San Francisco, all trying to use your app at the same time? You can't just put a server right next to every single person on Earth. So you've got a problem. And that problem is called latency. It's that annoying delay you feel when you're waiting for a website to load. And it's caused by a simple, unavoidable law of physics. Information can't travel faster than the speed of light. Sending a signal from London to Tokyo and back just takes time. And that delay can make your app feel slow and clunky, no matter how powerful your servers are. So to fight that latency, you put copies of your data closer to your users. But doing that creates what engineers call the impossible choice. See, in a perfect world, you want to promise three things. First, consistency, meaning everyone sees the exact same data at the exact same time. Second, availability, meaning your app is always online and working. And third, partition tolerance, which is just a fancy way of saying the whole thing doesn't fall apart if the network connection between your data centers breaks. And this is where we run into a fundamental law of distributed systems, the CAP theorem. And what it basically says is that when that network connection eventually fails, and trust me, it will, you are forced to make a trade-off. You have to pick two of those three promises. You can choose to keep everything consistent, but that might mean some users get an error message until the network is fixed. Or you can choose to keep the app available for everyone, but that might mean some users see slightly out-of-date information. There is no perfect answer here. Every single large-scale system has to make this tough choice. So we've gone on this incredible journey through these huge technical challenges, but the book doesn't stop there. It ends with a really crucial pivot, because once you've actually built this reliable, scalable, globally distributed system, you're left with a totally new and much more human kind of challenge. Because the systems we've been describing, they don't just handle abstract data. They handle the data of billions of individual human beings. And that's not just some technical achievement, it's a really profound social responsibility. This quote from the book just gets right to the heart of it. Behind every single row in a database, behind every data point that gets collected, there is a person. And the book argues that because of that, engineers have a real duty to think about the human impact of the things they build. And this leads to some really tough questions the book brings up. If the data we feed our algorithms is full of historical biases, will our AI just learn to make those biases even worse? In our rush to personalize everything, are we accidentally building a massive system of corporate surveillance? And when we all click I agree, do we really truly understand the vast and complex data machine we're plugging ourselves into? So we end here. The quest to build a perfectly reliable, infinitely scalable system is for sure one of the great engineering challenges of our lifetime. But as we get closer and closer to that goal, we have to stop and ask, what are the trade-offs we're making along the way? And what is the human price we're willing to pay for technical perfection? And that's a question not just for engineers, but for all of us.